This is part 2 of a 3-part series. Thank you for being with us. Your time is valuable, so I hope you get the most from this. This part is choosing the adapters, low capacity force measurements, and potential measurement errors. My name is Henry Zumbrun. I am the president of Morehouse. This is my contact information. You can also reach our sales team at info@mhforce.com. Please feel free if you have any questions or comments or whatever, feel free to email me. I'm always happy to answer questions. Our purpose, I like to state this because what we all should be doing if you're here and making force measurements, we create a safer world by helping companies improve their force and torque measurements, but we're all doing that, really. If we can improve our process, we're going to improve the safety of everything. You know, a lot of times we don't know what these instruments are being used for, you know, and where the metrological traceability transcends to. It could be something, it could be the brakes, it could end up with brakes for your car. And if they fail, it's not going to be a good situation if the brakes from in your car fail because of a bad measurement. If a bridge collapses because of bad measurement, all this stuff, just what we do, the measurements we make are very impactful on society. If anybody is interested in those impacts, Henry Petrosky wrote a book, To Engineer is Human. I highly, highly recommend that. So when we start talking about the importance of adapters, we're talking about keeping the line of force pure, free from eccentric forces, and it's the key to calibration of the load cells. And ASTI ME74 does not address it, but ISO 376 does. They talk about the adapters that is needed to keep the line of force pure, and they give you recommendations in their annex. Just a really good document. Those that are calibrating to ISO 7500 should know ISO 376 quite well, because that is the standard that you need to have to perform calibrations in accordance with 7500. Just a further picture of a misaligned load cell. My owners push me, pull me, side load me, twist me, distort me, and they do not care if my load path is right. And then, yeah, a blurb for us. I've been to Morehouse and like the way they treat me. If I use Morehouse, all my problems would be solved. But this is really, there's quite a bit of truth from this. It doesn't have to be Morehouse. It just has to be consistent adapters. It has to be adapters that are proven. So it all depends. Again, it's a situation of risk. It all depends on how much risk. These are adapters here that we know work. We know they work well. The ones on the left have a spherical radius. The ones on the right have a ball seat. Now, if we're putting these in compression and then they're going to go in a machine and the standard's going to stay in compression, the one on the right is far superior. It aligns the force. The contact point is small. There's very, very low friction loss. That's not always the case. That people can use the ones on the right or have a ball adapter. So we made spherical load buttons for those that can't. And if you look at this, using a ball adapter and the machine has a ball yields the best results. If a ball adapter does not exist, then a spherical alignment adapter will help align the force. That's all we're trying to do, is get that first picture, getting that line of force pure, free from eccentric force. And then here's the actual section from ISO 376, recognizes the importance of adapters. This is the annex, A41. Load fittings should be designed in such a way that the line of force application is not distorted. As a rule, tensile force transducers should be fitted with 2 ball nuts, 2 ball cups, and if necessary, with 2 intermediate rings, while compressive force transducers should be fitted with 1 or 2 compression pads. This is a good first step in establishing some type of standardization across the board to say everybody should make these adapters. The cool thing about them is they can overcome about 1 degree, about 1 degree of misalignment maximum, but they can overcome a little bit of that. So you have a better chance of keeping that line of force pure if you're using these type of adapters with spherical. And we've adopted them. We have 2 sphericals in our adapters. So, but the wrong adapters, hey, I've been in this 21 years now, and coming in 1999, I saw some threaded rods still being used way back in 1999. Fortunately, we got rid of that pretty quickly. You could tell if you had a bad piece of threaded rod, you rotate a load cell, the results, don't come into alignment. They're actually, bad. You see high deviations, so it absolutely shows up in your calibration data, and it's whether you realize it or not. You kind of need to get what a good load cell looks like with the machine being plumb level, square rigid, and with load torsion versus a bad load cell. And then you need to figure out, was that load cell bad or were the adapters bad? Did the customer send in a bent rod? Because we measure them. So yeah, it's not good. Even straight threaded rod can introduce misalignment issues as they can distort the line of force and yeah, so not good. Threaded rod, everything wants to unthread. There are better things. Your eye bolts are another thing that people use. They can be okay, but you have to watch because there's friction in there, and as those bearings start to seize, or if they get hard to move, then you will have a problem. So, any misalignment of 0.1 degrees can affect the reproducibility of some load cells. In even our adapters, I said 1 degree, but we can definitely overcome 0.1 degree here. The 0.1 degree is the statement that we're standing by. The 1 degree is a bit of a little bit of a stretch, but here we have quick change adapters for force. This is in line with lean principles, if anybody's setup reduction principles. So you have one set of tension members, and then you have the various adapters, which makes it real easy to couple load cells and the like. So just a efficient process if you're having problems with setups. We also have with the ISO radius here, and that can convert to a clevis set. And here's the value kit here. If you order a full kit, there's difference. We improve alignment, simplify setups with one, fit for use with clevis, and rust resistant. The black oxide here is just a rust resistant. That's why all the parts are black. They're not painted black. They're typically made of steel, some form of steel heat treated to the appropriate temperature. And after that, we use a method called black oxide, which helps prevent rust. So that's why they're black. We were talking about ISO 376, and this is from the standard. And it says compressive force transducer should be fitted with 1 or 2 compression pads, and that's what we're looking at here. From the standards to the left, and then we have some of our stuff here to the right. And if we look at this in more detail, what does this look like? This is a recommended setup for ISO 376. Bit different than what people normally see if you're not accustomed to the standard, because again, they are calling out base plates and they are calling out top adapters. So we have truck scales. This is one of the measurement of errors. Picture showing 2 different size adapters. Will there be a difference? A lot of people don't realize this, that you're weighing an airplane or weighing a truck. Well, the footprint of the tire can be impactful. Again, when you're using the device, different tires are pulling up, right? A different airplane may be being weighed. Different truck may be being weighed. So the actual footprints of the tires may vary. And when you start asking, will there be a difference in measured values? Well, here's a scenario. We had a lot of truck scales come in, about 13 of them. So I got to take a lot of different data on this, large to small adapter. And if you follow me a little bit here, you can see what's going on. We have normal pad, and then we have small pad. So those 2 things right there that I just highlighted and kind of painted over, but those 2 things, the normal pad would replicate the size of the truck tire. The smaller pad was, exactly what I said, is smaller. The tolerance on this was pretty wide. It was a 1% tolerance. But if you look at the difference of using the pads, down here, we're at 70% difference. And you can see as it's creeping up, as you get closer and closer to capacity, we're 140 pounds of that tolerance is used by switching the size of the adapter. Now, if the spec on this were 0.1% or a half percent, and we had this much change in adapters, it would not meet spec. And believe me, we've run enough aircraft and truck scales and done the simulation enough time that they are all over the place. So you really need to test. The best thing you can possibly do is buy adapters that have rubber on them to replicate the tire. So if you're doing any scale calibration, again, find out what that tire footprint is, find out what the manufacturer recommends for calibration, and standardize your process accordingly. Here's more blown up of the actual error. So that we just talked about with that difference. Uh-oh, I drew on this and I don't know how to get it off, but we'll figure it out. Here's another test scenario here where we're another test scenario here where we're using a aircraft scale, a different size scale, and we're using different pads. Here you can see it blown up, and the difference in this scenario, the difference is quite large. You know, at 40,000 pounds with the large pad, the one scale reads okay, real close, 40,010, where on the other end with the small pad, the meter saturates. At 36,000, we have a 1.30% error. That's, you know, that's very, very large for what we're talking about. It's way over the specification limit of this particular one. And if you had the varying size, you know, truck scales or varying size footprints, this scale is all over the place and probably does not have what is needed to make or standardize that measurement. And when I talk about the rubber, this picture here, this shows this. We make a lot of these adapters here, and the whole point is you should really replicate that tire footprint. If this were 100% right, we'd have an oval. If we really wanted to do it 100%. This happens to be the model that we've adopted for this one. We have done ovals and we have done circular footprints as well. This is the standard one for the intercomp scales that they recommend, the manufacturer recommends. So again, replicate the tire if you can, or go back and look at and see what the manufacturer recommends and follow that recommendation. The big thing is just to make sure you're consistent and standardize the process. Best practice, importance of adapters. Best practice is to send any top blocks or plates with the load cell being calibrated. Each load cell should have top blocks and they should be ground flat. Using tension adapters with a steep spherical radius will provide better vertical line of force, producing better results. So this is a live session on here. I left this in just specifically. If anybody wants to comment down there in the chat window, we'll review it later. Did anyone learn anything new so far? And some takeaways. You know, if you're doing truck scales, what's your takeaway? Are you going to go back and are you going to make sure you're standardizing that you're using the right adapters? You're not stacking just a pad on it, because it's going to make a difference. The data there clearly shows that you're going to have an error if you're using X size and the customer's using Y size and they don't match. All bets are off. So I think last week we talked about choosing the right load cell. I want to talk about a little bit about choosing the right indicator. Here's 3. Here's a 4215. This has a display. It can go millivolts, pounds, kilonewtons. Can be set up in whatever unit. That's this one right here at the top. That's a 4215. Then we have our Hattie. This is probably my favorite indicator, high accuracy digital indicator, less expensive than the 4215, true 6-wire system, which we'll talk about later, and all around good, just really good filtering, really good meter. The disadvantage is it requires a computer. As you see, there is no readout here. And then we have this one that's a little handheld 2-channel one on batteries. Works well if you're doing a verification check. Really not the greatest for calibration, but really good if you had a press or you just wanted to put a load cell in something and see what the force was as far as a check standard. So you just kind of have to go through. If you're looking at meters, the best thing is, you know, linearity is going to be something to consider. How good does the indicator need to be? You know, you do everything right. Buy a good load cell. You know, have it calibrated with deadweight primary standards, and then go out and look at indicators and buy the cheapest indicator. That's going to automatically be most likely be the weakest part of the system. So you really need to spec it out. This indicator right here is better than 20 parts per million. Here it says, does it need to be better than 50 parts per million? So yes, it does. This one is 20 ppm linearity. Are you willing to use a computer to convert the millivolt to volt to engineering units? Some people say, hey, I don't want my technicians using computers. I want it all there. Fine. It's just a matter of, again, it's just the decision tree that, what's best for you and your application. Do you require portability without a power adapter? Okay, yes, you can do that if you have a laptop. Do you have more than 2 load cells? Multiple systems, but then you have a whole thing of risk. If you put too many load cells on one indicator and the indicator fails, now you have that risk of having to have the whole system recalibrated unless you have a backup indicator. However, having a backup indicator requires traceability, and I'm currently writing a article on that and what needs to be done. And there's like 10 steps that need to be done if you want to go down that path, because you're going to need to standardize it. You're going to have traceability on the standardizer. You're going to have to make sure the uncertainty is less than like 1/10. Between the 2 indicators, and it just takes more. It takes more effort to have a backup sometimes than what it's worth. I like to see, my high recommendation is, if you have 3 load cells, is to put one of these indicators on each of the load cells. Then guess what? They each have their own indicator. If something goes bad, you can still use the other 2 load cells and only send one back. If it's load cell or indicator. If the indicator goes bad, it's only one load cell you have to have recalibrated. You don't have to worry about the headache of a backup. You only have to worry about that one cell. And you can, if you're running a group, you can easily continue to function with the other load cells. Sometimes if you have enough overlap, you can get by and schedule jobs appropriately. And these, typically on most of these, you can have a replacement in less than a week, new cal replacement in less than a week if push came to shove. So maybe that's not the indicator for you. So then you start looking at a PSD. This is a portable indicator, 1 or 2 load cells. It only has 2 channels, or it's close to direct reading, which means at 10,000 it may read 9,998. And you just have to know that you have that bias. You want portability with batteries, and then you have the 4215. This is probably one of the more common ones, because people like to have the display. In general, that's what we find. Do you have more than 2 load cells? Do you want to span multiple calibration points? Good indicator for that. But yeah, when you're evaluating things, you choose an indicator based on your accuracy and uncertainty requirements, choose based on environmental conditions, choose based on 4 or 6 wire sensing, based on price. I mean, everybody's looking for price. That ASTI unit really, that stacks up with some of the best indicators. It's very value 6 wire system. Choose based on ease of use, ruggedness. Again, on that ASTI, I don't want to do a disservice to it, but it's in a case. Most times, what happens is people break the case and not the actual indicator, which is okay, because you can replace that. Choose based on the number of load cells and channels required. On a millivolt per volt indicator, you could have multiple. You could have 20 load cells, but then it's how risk tolerant are you? Are you okay to have one indicator with 20 load cells? That's a lot of risk stacked up, unless you're doing the appropriate backup methods. So that's on indicators. Hopefully you can pair that with the load cells we discussed last week, and you put it all together and get yourself the system of your dreams. But now I wanted to talk about low force calibration problems. And here's a handheld force gauge calibration. Some of the problems we have, typically if you're using weights, you're stacking weights, off-center loading, and you have safety issues. If anybody saw a post I made, it's about these back plates. We were making them in our facility last week. We've had customers come up and say, hey, I've stacked weights and I've dropped them. The one guy was, and maybe that's you on the webinar today. The one guy was telling me he had weights drop and he saw it just roll right by his foot. He said he just watched the thing drop and he watched it roll right by his foot. And fortunately for him, it rolled by his foot, right? That doesn't happen with everybody. If you drop a 10-pound weight and you hit your foot just right at the top, we're talking beyond steel toes. Steel toes are fine. You can say but if you hit above that steel toe at the top at the right angle, you could shatter that bone very easily. I was at a gym one time and someone pulled a 10-pound weight, dropped it on their foot, and someone came running over to him and said, "Are you all right?" They were in a horrific pain, but they walked it off. And the guy said, we were all like, "Well, why? That happens. People drop weights." And the guy had told us there that he had been around somebody that had dropped the weight and it had shattered their foot, and he was coming to see if he needed help to carry him away and get him to the hospital. So very concerned person. Luckily, it wasn't to that extent, but it can happen. So something to know about as far as safety and ergonomic issues. Slow and dangerous, yes, very much. Ergonomic issue, you got to play Jenga. I like playing Jenga, but I don't want to play Jenga with stuff that's going to fall and going to cause me damage. Often not corrected for force. This is the other problem with weights. You have mass weights, and force weights require the correction for gravity, material density, and air buoyancy. So if you're not correcting for that, you could have really, really large errors. We have an app. We have a blog here. This presentation will be available to everybody. We have a blog. It shows these errors are anywhere from 0.5, which may not be a big deal, but if it's a 0.1% device, you're eating up half of the specification. Half of that accuracy, half of that tolerance being eaten up if it's 0.5, up to 0.185%. That's in the United States. I think the worst case scenario was like PA to Alaska. I don't think I did Hawaii. These are just examples that I found with true gravities and just using mass in place of force. So this is from a great paper, that the gravity of the situation by Philip Stein. As I look at the CCT primer on my desk, Philip Stein was the author of that. For those that don't recognize the name or may think they know the name, very, very unfortunately, I did not know him, but I've read his papers and they are all pretty fantastic. So what he goes on to say is the effect of not doing this of the gravitational value, the effect of not doing this variation in the force produced by the weight of perhaps 0.1%. I just showed 0.1818 or more of reading is therefore strongly recommended that you establish the local gravity for your laboratory and use weights that have been calibrated at that gravitational constant. Ideal solution is to have gravity measured on site by a National Geologic Survey Agency. And then here's from Phil. There are several formulae usually based on latitude, sometimes altitude above sea level. These are quite inaccurate, often being incorrect by 800 to 900 milligals or about 0.1%. Obviously, these may be used if a stated uncertainty of a measurement is corresponding course, but it's not a good idea. So if you wanted to do it, the exercise here's the formula. It's M is the mass of the weight, G is gravity at a fixed location, D is air density, and big D is material density. Conventional mass is the conventional mass of the artifact, is defined as the mass of material of specified density that would exactly balance an unknown object if weighing were carried out at a temperature 20 degrees C and an air density of 0.002 grams per centimeter cubed. Again, this is additional blog. This is here. I use Denver in this particular equation. So if we had 10,000 pounds, we find our gravity. We could find the air density and material density, or we could use a conventional formula. Best to use if we had the material density. It's better, assuming stainless. Stainless you often see 8,000 kilograms per meter cubed, but in this one we're finding if you use conventional, you'd find that. But here's the real values, and if you plug everything into that formula. At the end of the day, you have a mass. If we had the force value of 10,000 pounds and wanted to convert to mass, we'd have a mass value if we were going from York, PA to Denver of 10,011. If we were making a machine for somebody in Denver, a dead weight machine for somebody in Denver, we would adjust accordingly. So the mass values to produce the right amount of force would be in this ballpark. 10,011.89 would actually be the mass that they would apply to generate 10,000 pounds of force. And when you think about force, the easiest thing, and one of our very good friends, Mr. Bird, I'll give a shout out to him. We were talking the other week from Tinius Olson, and I loved what he said. He said when I explained, force, he said, you have a ball, a squishy ball, and to compress that ball, it's the same amount of force anywhere on the planet, virtually. That your hand strength in compressing that ball, it will be the same amount of effort and force anywhere on the planet. And that's with mass. That's just simply not the case because we're dealing with different gravities. But force is mass times acceleration, and therefore you need to know what the gravity is to know the force. But you can do that. There's GeoPlanner, there's other tools. You know, the expanded uncertainty, if you start using that, or I'm going to say we have an app for that. That's, you know, I just queue myself up for this great thing. But you can hire survey firms, you can do other things. But in essence, if you do these things in this presentation and you want to convert, you know, force to mass or mass to force, you can be within about 5 parts per million just from using NOAA. And that's what our app does. Our app goes there. This is free to download in the Android store. It will soon be available on Apple. Apple version should be out by June. It's free to download. What it will do is it will use as a GPS signal, and it will get your location, and it will go to NOAA and plug in all the values. And from that, you know, there you can see gravity from NOAA's. So we're going right to NOAA. We're getting the GPS of your phone, and we're going right to NOAA and doing everything for you. And it's also a converter. We tried to put in the majority of force. You know, some of these I don't see a lot of, but we try to put them all in. So if anybody wanted to also do that conversion, really, you know, and the device tells you your latitude, longitude, and altitude. But again, GPS has to be enabled. The complaints we've had from the app or doesn't online is it doesn't work, and you're like, well, if you're in a basement, it's not going to work. You need to have a GPS signal. So that's the only thing I can tell people about that. Other common problems, off-center loading issues. Most handheld force gauges require different centering fixtures for alignment. If the line of force is not pure, a large measurement error should be expected. I like this picture here, and it shows you what I hate about these force gauges. All the different manufacturers, right? When you see the kit that we need to provide, they've done a bunch of different hole patterns, which I'll show you on the next slide, and all of them have different centering distances. And when we look at the centering distance, what we're talking about is that difference in here where I drew the line to the back of the bracket. This is another case where if somebody would have just sent an industry standard, life would be so much easier for everybody trying to perform the calibration. We now have close to 15 different centering spacers, and that's just this piece down here that I circled. There's that much variation, and the back plates are all over the place. So here's pretty much a full kit. This one does the majority of force gauges, and you can see these centering distances here. Look, even in this picture right here, you have 11. Since then, we've added more. So, and look at all the different hole patterns. Now, to me, if they would have just standardized it, we could have one freaking bracket. You know, they could have different size, a couple different standardized hole patterns. You could have one bracket, agree on one centering distance, and be done with the whole thing. But they didn't do that, so we're left with what we have. Here's a kit. If you're running a Cal Lab, this is a really good kit if you want to do handheld force gauges walking in the door. They simplify setup and reduce errors with stacking weights. The shown here is our PCM, our portable calibrating machine, under 2,000 pounds, really good, eliminates the ergonomic issues and everything else. So the other thing, misalignment can cause errors that exceed 1% of applied reading on certain load cells and other devices, and just using the right adapters will help reduce these errors. Like, you really have to center this machine. So if you're looking at the low cost thing, value proposition, low cost compared when paying someone to manually lift weights onto a pan and take a reading, that takes forever. So you have some cycle time. You can recoup some cycle time, cost benefit. Low cost when comparing against technicians sustaining an injury. I would never want to lose my best technician because they dropped the weight on their foot. That would be just horrible for everybody around and can be easily prevented. Low cost when compared against other systems that are not versatile or have the proper adapters. Yeah, no one really ever evaluates, you know, what it does to the end user when you have high uncertainties, and they never evaluate what the wrong adapters do to the measurement chain. And I can tell you that if your measurement's off, that bias will carry through to every subsequent measurement down the chain, and it will get worse and worse and worse and worse. So this machine here provides the user with fine and stable control of the applied force, offers a large working area to test, you know, various load cells, and you know, we can send shear web, S-type, force gauges, button, beam load cells, all types of different ones, handheld force gauges. Everything else has been put in these machines. You know, high value when compared to paying someone to manually weights, high value, you know, versatility. We've seen the system have an accuracy better than 0.05, better than 0.03 is achievable. Now you have to be careful down here. This often requires multiple load cells. There's manufacturers out there that spec these accuracies, and they'll say something like, "Hey, my system is accurate to 0.05." So when we say our system is accurate to 0.05, that often means that it's accurate to like 0.003% at full scale. You know, I didn't put full scale in there. You know, people write a full scale. Well, full scale is really difficult accuracy wise, because there's a number of factors when you start looking at uncertainty to go in. So if we're at 0.003 at full scale, typically you could say, hey, at 10% we'd be at 0.03. Yeah, that ratio doesn't always hold because there's different, you know, resolution. Some things become dominant. Remember, when you're doing uncertainty, you're putting everything together to make up that uncertainty. So speccing it at full scale is pretty rough because it's not always the same, and it does not scale down in a linear fashion. So watch that. This implies if you want better than 0.03%, said it's achievable, that means you're changing a standard at about every 20% of the range. So you have a 1,000-pound load cell, you're going to get better than 0.03. You're going to get 0.03 probably at 20%, and you're probably going to get like 0.00, you know, 3.2 at capacity. So who knows? You know, numbers on those range. You just have to run the data, have to run repeatability, have to run all that stuff. And once you run all that, then you can really know. But when we say this, just know that 0.03 is basically saying that you're going to have two standards, and you're going to switch them out. And be wary of people that tell you accuracies of 0.0005 of full scale, 0.001 of full scale, because what does that mean? And be wary of, you know, at the 10% point, what that means, because it does not always scale linear. In fact, my example is good. If we had 0.003 at capacity, and I'm saying 0.03 at 20%, that's not linear. 0.03 at 10% would be linear. So that's really where it is. Anybody, some people, this is not that long of a section. I wanted to get this in here. This is cable tensiometers. I know not everybody calibrates them, but they are often neglected, and they are very, very important to understand what's going on with them, and then understand the equipment to calibrate them and your current challenges, because they don't always repeat. I've looked at a lot of people's measurement procedures on these tensiometers, and it's like, take 7 readings, throw out, you know, take the best 5. I've seen that actually in a procedure. So that tells you something when you're removing 2 out of the 7. But a cable tensiometer, for those that do not know, is a device with an accuracy specification that is typically 1 to 5% of capacity of force. They are used to check the tension of wire cables, typically used in aircraft rigging and textile manufacturing. They use a force gauge to react against the cable via a riser and display the result through a gearbox onto a dial scale. The dial is often just a linear scale numbered 0 through 100. A conversion table is then drawn up to convert the number to a meaningful result in LBF, KGF, Newton, whatever you're using. So calibration is often done by loading the same force point several times and taking an average of the readings, or throwing out some readings in some procedures. The tensiometer should be calibrated based on use and other factors. Some common problems to watch are for physical damage. Overstretching of the spring can happen when the correct riser is not installed for calibration. Corrosion and damaged risers. You're going to put pieces in here. And here's fun stuff. You look on Google, and Google tells you, hey, you can calibrate a tensiometer this way. Some calibration procedures may be very questionable. Yeah, weight bucket's a questionable one. A common method of calibrating is fixing one point of the cable and stacking weights, or even filling a bucket with the appropriate amount of weight to generate the force. I saw this, people using it, that's fine. As funny as it may be, if someone's looking at it and saying it's funny, if you know your force values, you know the weight of the bucket, you know everything else, maybe this is an acceptable method. I think it's certainly more acceptable than using a torque stand, because if you use a torque stand, remember, torque is force, times length. So in that, you're going to have to backtrack a bunch of calculations that never make sense. You're going to have a rigid cable. You're going to be doing it at some kind of, vertical plane where a lot of error could just happen. I am not a fan of using a torque system to calibrate tensiometers. That's just, you're asking for problems. You're asking for errors. This is not the greatest either. Obviously a weight bucket, but, it's something. I mean, if anyone thinks the weight bucket is metrology sound or we're passing audit, I don't know. There's probably some auditors out there that have seen this being used effectively. You would have to me, you have to calibrate. You have to get values for everything, and most labs are probably not doing that. We do have a solution. We built a mechanical tensiometer calibrator. It's a modified PCM. It goes to 2,000 pounds. It's got 5 feet in length. And we also have smaller models if the 5 foot is too long. Very tall machine. What you'll see different about this is this safety glass here. Hey, cables break. We know cables break, so this is made with the safety glass installed, load cells set up there at the bottom. It's equipped with several time-saving features that enable a quality force calibration on a wide range of force sensors. Shear, you can do everything you can do with the PCM. You can do handheld force gauges. You can do everything in this setup. I like this machine a lot for calibration of tensiometers, and it's low cost when, I know what people are doing. They're manually lifting large weights onto a pan, which is great for conditioning, strength conditioning, bad as you get older and your joints and everything else and ergonomic issues come into play. Typically, the dead weight version of these tensiometers is about 90,000 plus, so this one's a lot lower cost than that. Low cost against injury, low cost when compared against a less accurate method of back calculating torque and not getting the right result. Again, I'm not a fan of back calculating torque. You cannot convince me that works. I need to come see that and take readings, and I can poke holes in it all day long. High value when compared to paying someone to manually lift weights onto a pan. We can calibrate everything. And this system has an accuracy of better than 0.05%. And again, that depends on the number of standards used. And the ranges that you want to achieve. Here you can see the full setup with the tensiometer in it. There's a window in this. See the window there? The technician can reach in, get the tensiometer reading, and they can do this. It's not very problematic. What is interesting though is that you're dealing with 2 fixed points. So when you use this method, what you're normally doing is you're loading. You want to apply 500 pounds of force. You load to about 460 pounds of force, then clamp the cable and see what happens, because that you're shortening. When you clamp the cable, you're shortening everything and you're creating more pull onto the load cell. And in fact, a lot of tensiometer cals with everything's measured 2 fixed points. So my argument is when you have only 1 fixed point, it really doesn't replicate how they're being used. Guidance document, calculating force CMCs. We have, NCSLI RP12, we have ASTM appendix, and what we did is we combined that ASTM, some of the appendix, with A2LA R205, and I should change the slide. We have a guidance document. It was published by A2LA. It's in their G series. You can go right now to A2LA. I think it's G140. You can go right now to A2LA's website and you can download the G for free. You can download the guidance document that we specifically wrote. We had help from several other great people, but the majority of it is from our blogs, posts, and teachings on uncertainty. So really, really proud that document was voted in and that document is out there for everybody to follow who wants to talk about uncertainty. So we'll talk about it a little bit. Because we need to understand uncertainty, because when we start talking about force measurement errors, how are they going to impact your uncertainty budget? So as everyone's there, you're thinking, what goes into a certainty budget? You know, you have your calibration. Some people are going to say, hey, the accuracy of the load cell, the specification sheet. They're going to say a lot of different things. And I've yet to find people that have consistent answers that we have not trained. So the people that have been in our training know very well what goes in an uncertainty, because we have several examples. We do budgets in our classes. We have that, and we have that online too. We have an hour-long webinar on this uncertainty. But what we do, if we're looking at ASTM calibration, the biggest mistake is people say, hey, I'm going to use SEB nonlinearity hysteresis. This comes from assessors too. You know, it's coming right out of that NCSLI RP12 document, and it's not right. If you're using ASTM, you don't care. We don't care about SEB. We don't care about nonlinearity or hysteresis. We just don't care, because the standard is going to give us a quadratic. They're going to give us coefficients to fit a curve, and all that goes away. If we use those coefficients, we're going to match that force point almost exactly. Just wrote a paper for Cal Lab on this topic, millivolt per volt calibration curve versus 2-point span, and there was like a 2,000% difference. I mean, we're talking small numbers, so be cognizant when I say 2,000%. You're talking, you know, 0.2 to a 0.01 type scenario, but it's still a big, it still can be a big difference on the load cell. So what we're going to do, if we're looking at uncertainty contributors, you look at type A, you look at ASTM lower limit factor. You look at repeatability of the best existing device. We look at repeatability and reproducibility. Resolution of the best existing device. Reference standard resolution. Reference standard uncertainty. Reference standard stability. Environmental factors, other factors. Down here, the type B, the easiest way to remember these are you know, we're looking at 5 R's and an E. And you say, wait a minute, there's only 4 R's there, but we're looking at, we're adding the repeatability from up top. So in essence, the 5 R's and an E is a good tool to remember. This has more as we are doing more in this analysis, but as the bare minimum, 5 R's and an E. So if you're going to do this, you're going to need the calibration report for the device, the uncertainty of the instruments that were used, calibration history. You're going to want to, people often forget stability. We need to know. We have one customer that every year they send something in. I want 0.1% accuracy. Okay. Every year we adjust it. On their scope, they have 0.1% accuracy. Does anyone in this audience think if we're adjusting 0.1% every year, how in the world can they claim that they're 0.1%? They're not taking stability into account, because it's drifting out of specification. So that you really have to, that reference standard stability is key. And a lot of people forget it. Manufacturer spec sheet, use them for environmental. This can be for other error sources as well. If you know you have some side load, maybe you can quantify it in there. And then other error sources if known. End user, so that we get asked this, you know, can you do an uncertainty budget for me? Yes and no. I mean, things you need to do, we can do all this stuff. We can pull most of this for anything, right? Error sources, we're going to have to ask a lot of questions. But in the end user will always have to conduct their own repeatability study. They will always have to check the repeatability and reproducibility between their technicians. And you're going to have to complete some type of proficiency testing requirements, which wraps it all together. So how do you know your measurements are as good as you say they are? The only way to prove it is through proficiency testing or doing an ILC. So the best thing is, if you're out there and you're wondering, hey, you know, I'm seeing this, I'm wondering if I'm generating the appropriate amount of forces, you can absolutely call us. We could lend you a cell, you know, do the calibration. We could calibrate a load cell in dead weight, do the calibration, send you the data, and you could do a comparison on your own to know if your system is good or not. That can be for force or torque. We also have this Excel sheet. And I think I have a crowd that a lot of people have seen it, but if you haven't, it's available on our website. You can download it here. Here's another good example, back to the lab that claims 0.05% of full scale. Now, I can sit there. This is with one load cell, not two. This is in our PCM. This was controlled. This was done for a class where we had people in class and we took the results. Every time we do this, it comes out a little different. The one at the top, not so much. So at the top, I can here I can claim 0.005% of full scale. At 10%, that should be, 0.05, should it not, if we just scale that down? In this case, it's actually lower, but that's all dependent on how good, if I go back, how good the repeatability is. And if you look at this repeatability, it's darn good. But if we have an unexperienced tech, that repeatability could grow. So there's lots of different factors and contributors that all go together that get weighted. This uses the Welch-Satter weight equation that get weighted with the appropriate degrees of freedom and everything else. And really, this is a really good example of that you can't just linearize your 0.005% of full scale. So yeah, you really have to run the numbers and test. So we're running into the identify potential force measurement errors, implement proper force calibration techniques as discussed and demonstrated in this webinar. And here's the heart of it. Like, here are the major ones. We're talking about, here's the 20% that gets you 80%. These are the major ones. There are more than this, but these are the ones that look out for. Cable stiffness and mounting, using mass weights instead of force, showed you that earlier. Misalignment, different hardness of top adapters, thread depth, loading, cable length, bolting, and we're going to cover all of them. So right now we're going to start looking at all these different errors, and the first one is cable stiffness and mounting. Cable stiffness may influence the measure as it can provide a parallel load path. On smaller cells, this effect can be very significant. Often recommended that the transducer be oriented that the live end is mounted toward where the force is being generated. This is the live end of this transducer. I realize I need a better picture of a load cell with a big cable on it, because we see these BLH, great company, they make very good load cells, but their older load cells, they'd have like a 300-pound load cell with a really, really thick cable, which isn't generally a problem, but you have to support the cable. So not supporting the cable, 300-pound load cell, thick, heavy cable, that's going to slide in and it's going to distort the path of force. So just something to be cognizant of. Using mass instead of force weights, we covered that a bit earlier on what to do with that. Misalignment. For compression loading, a load pad or button can be used and the surfaces should be ground flat. We have shown large deviations on ASTI E74 calibrations by using a beat-up non-flat pad. For tension, it is recommended to use adapters with spherical to reduce additional bending moments. And then a well-aligned calibration machine may demonstrate bending less than 2%. Some transducers also specify this error. We're looking here on the spec sheet for side load sensitivity. The use of proper calibrations adapters are required to minimize this error. If you're using our UCM, a 1/16 of an inch possible misalignment, that equates to about a 30 parts per million error. If we're looking at in general misalignment and what it does. Here's one you can see. Look at these two pictures here. This is just blatantly, we're going to show you blatant misalignment. And the reason I'm showing this, and I hate doing this over a webinar because I know it's a bit blocky, but you can get the gist of it. We're showing deliberate, alignment versus misalignment. We're not using the best adapter with a ball seat. We're not doing, this is not best practice here completely, but we just want to show, the purpose of this video is to just show that how forgiving the right load cells may be. And we certainly do not recommend anybody, deliberately misalign a cell. But if you're a tech and you're out there doing E4 work, you're not going to be perfect in that tensile machine all the time. And if you want things where you want load cells that are more forgivable for your technician, this is just one of them. They should still absolutely pay attention to alignment and everything else. But right now, the person applied 3. They aligned it visually. This is a good visual representation. And now they're really, that is really misaligned. Look at when you look at it tip, when that force comes down, it tips all over the place. So they should have tared this before it came down. That's a little bit backwards, but they tared it. I had an intern edit it, but they tared it, and then we're getting millivolt readings. They're going to take these readings. You're going to get 3 sets of millivolt readings, and they're going to compare them. And going to compare that really, really misaligned load cell with what we considered having pretty good alignment. And this is sped up. If you're paying attention, someone had a Penn State shirt on earlier, and now they have a different shirt on now. So, but look at this. I mean, align versus the difference. Only 9 counts at the 5th decimal place. That is a 22 part per million error. That is not high at all, and that is really deliberate misalignment of the load cell. Those that were there last week probably saw the S-beam, and when we do the same thing with an S-beam, but we only slightly misalignment, we show that there's a 0.75% error versus 22 part per million. What that effectively does on the S-beam, it raises the uncertainty by a factor of 10. On this type of load cell, it raises the uncertainty by a factor of like 0.2. So 10 times versus 0.2. We had hardness of a top block. We had a customer send in a 1 million pound load cell. I've been in the lab technician for years and years and years. This one got me. So you get pretty biased when you work in a lab long enough, right? You see the same load cells come in. You kind of know what to expect. You say, oh, hey, I'm going to put this in the machine. I'm going to have a pretty good cow. I know this. I have history on this cell. I did it last time, got good numbers. So it's pretty simple. You just go set it up, do everything right. All of a sudden, you set this up, and it's 1,500 pounds off. It's like, that doesn't make any sense. Year after year I've done this, and it's been a pretty darn good load cell. Why is it drifted that far out? So you start saying like, hey, did a strain gauge, is it coming loose? Is something weird? Are my connectors anything else? And is it stability or an adapter issue? Well, prior to this, I had not really seen the effect of top adapters on a load cell, and called the customer on this and said, hey, we have a 1,500 pound error. And they basically tell me, oh yeah, about 6 months ago, I called the manufacturer and had new top blocks made. I've been using them with these other top blocks. I told them what was happening and said, hey, what do you want to do? This is 15. Well, I don't want it 1,500 pounds out. That was a pretty typical reaction. I don't want it 1,500 pounds out. That's that's a pain in the ass to correct. So called them, talked to them. They said they're going to send the original block back. They sent it back. Again, same manufacturer. The people that made the original top blocks made this second set. I can't stress that enough, because what we saw here when we tested it, the original block resulted in an output of 180 pounds at 1 million when loaded to 1 million. That I do not question. Customer does not get a call for a 180 pound shift on a stable single column load cell. They do not get that call. We see that all the time. That is very acceptable change. The 1,500 was a flag. So doing this, getting this info, plugging it back in, knowing, teaching classes, plugging it back in. When we use the new adapter and we figured our difference between the top blocks, the customer's actual expanded uncertainty would have been about 269 pounds with the original adapter. However, since they switched away from that adapter 6 months into the cow and then sent it back in, their uncertainty went to 1,490 using the newly fabricated adapter. That is considering the difference between the deflection of those adapters. You can say, hey, it's 1,500 pounds out. Wouldn't they have been out 1,500 pounds? Well, not really, because it would have been 180. It was out 180 anyway. So we're just looking at that difference. This happens. Customer sends it in again. Different load cells this time. This is different setup. This time I took a lot more pictures than just giving the story. But here's with the customer's adapters. Customer sent this in without adapters. We reported the difference. And then I started testing. I said, well, let's just test. The customer sends it in. We use our adapter here versus what the customer uses. And I know several labs are not using the top and bottom blocks. They're using their own adapters, which is so wrong on so many levels. But it's, when people don't send top blocks in, this is the problem they get into. They just send a load cell and say calibrated, and we say, do you have top blocks? And they say, do it with yours. That's the problem. I'd rather never do that. I'd rather always do this situation where we have a top block and they know it. But this example, look at these differences. Same day calibration, same load cell. I did this over multiple days, different top blocks, tested R&R, and at the end, you can see these different top blocks change the output by as high as 0.3%, just because of the hardness. And you could say, how is that? And these are the 2 points we need to make. Material with different hardness experience different amounts of lateral deflection under the same amount of load. This causes different amounts of stress between the block and load cell. And then we have flatness and smoothness of the block is important in that it will change the contact position on the load cell. The assumption is that the load cell has a radius of maybe R17. That's a good one if you're designing load cells. And it's designed to be loaded exactly at the center of the spherical section. But an unbalanced or non-flat block can shift the contact point off center. As the stress analysis on the left shows, a small amount of shift will change the stress distribution. The key is to use the same adapters in use as used in calibration. The adapter should be manufactured not to produce off-axis loads. So a beat-up adapter is not going to work because you can get off-axis loads, but the adapter, if you can get it and design it right with that steep radius, there's going to be less contact. If your adapter's soft, it's going to deform. It's going to contact more of the load cell, and it's going to see more stress. So really, really important on this one that you use whatever adapters you want to use, right? You make sure they get to that lab with the load cell. Otherwise, all bets are off. That lab can give you a measurement that says, hey, this is the best load cell in the world. We're down to 20 parts per million. You've changed adapters and you could be at 0.3%. So really good word to the wise. Here's another video. I do like this one a bit more. This one's thread depth error. And when you say thread depth, people are like, yeah, what do you mean? So everybody wants to buy a load cell. They want to buy a shear web load cell, but for some reason, they don't want to install the integral adapter, height constraints or whatever. That's where, if we remember back to the spherical load adapters that I showed with the one with the ball's good. But the spherical, if you can't use the ball, spherical's better. And why is it better? Because we can control that thread depth, right? We can put that spherical in and we can load it against the shoulder. In our lab, and you as a customer, you can replicate that. You can consistently do it. The best thing is to lock an adapter into place, but not everybody can do that. So here, we're varying the thread depth and we're recording the different outputs. That's all this video is doing. So you could say, hey, I have an adapter that has, it's a 5/8 inch hole. I have an adapter that has this much engagement, or I have an adapter that has this much engagement. If you're loading through the threads, you are going to have high errors. That's just simply right there. There's the two differences, significant. It's going to be. So there's the differences. Now they have more engagement. That's going to change the amount of stress. I should say the amount of strain, because that is appropriate. So the strain gauge is going to measure that. You're going to engage more of that actual area, or you're going to engage more of that thread in that cell, and your output's going to vary. And here it is. I mean, if we look at the change, you have right here 1.97924 versus 1.97516. Quite a large error. When we do this in class, this was a tension setup that we did in class for people, and we do it live. You can do this live too, and we had a 0.034% error when we did it in class. But if you look at it, this is our baseline here on the right. If we're looking at expanded uncertainties at the time of calibration, 0.462 pounds would go out the door no matter what way we loaded it. But if we varied that engagement, or the customer did something different than what we did. We used a shorter thread. They used a longer thread. That 0.462 becomes 3.953. So not too much change at 2% point, but you can see this gradually grows bigger and bigger and bigger. And then hence this curve, which is one of the things I did early on, say, hey, if we load against the shoulder, this is my curve. It bumps a little bit. It's about a 0.01% different. If we load through different threads, look at this thing take off on how much the difference is. So not good practice. Loading against the shoulder is good practice. Best practice is installing an integral adapter and leaving it the heck in there. We like to sell these with the integral adapter installed because of this. This is the main reason. I want to provide something where you can have confidence in the measurements you're making. You can do it either way. It's just if we supply it with the adapter locked into place and you use it that way, it's more idiot proof. If you take that adapter out, you really need to be cognizant of what you're threading into that cell, how you're threading it in, and you better have the lab replicate what you're doing, or there's going to be all types of error. What about non-shear web type cells? Different thread. Some may have seen this. Sensitech cell. Nothing wrong with the load cell. Good success. I just did a test. Used these two different adapters. It's all the same thing, really. Difference of 59.2 pounds on a 10,000 pound load cell. Just varied these adapters. Customer said use your adapter and report what you want. Report what you did. We basically said, hey, we had about 1.5 inches of engagement. The problem is, like, it's random. Like, how do you each time, if you're just, if you're not loading against the shoulder and have an adapter, how do you randomize? Someone's going to turn it off a quarter turn. Someone's going to turn it off an eighth. Someone might give 3/4 turn. So what this comes out to is, if we look at this on the measurement uncertainty, if we look at this with the limits, specification limits, and we plot it out, expectation E74 cal, that first point, expectation is going to be, we want to be well within 0.25%. If we look at it, if this customer does this, TUR of 43, TUR stays the same, that's test uncertainty ratio. But if we look at this, all we're doing is moving the measured value. Everything else stays the same. So well within 0.25, you can see there's the point, a little off to the curve, but the specification limits, if they're trying to maintain the 4:1, do the E4 test, they can do it. Here, same curve, look, it's here's where we want to be, and it's way out there in left field. So it could go way out there in right field too, depending on what way and size of adapter used. But it's really really something to be cognizant of. Pick the adapters and lock them in place. If we look at the probability of the measurement, here's for all you statisticians, what is the probability of the measurement being within 0.25 if the top adapter is changed out? And you could say, well, looking from that, I should say if the top adapter, you see what's going on, and here it is. It's the same as hell freezing over. Does happen in certain areas of the world, but not often. It's just one of those things. It's just not good. So discussion here. How should we handle, you have this, how should we handle this known problem with a customer's load cell? And that's really what we want to discuss. Should we do any of these things? Call the customer, document it. Should we send them a postcard? There is a hell in the Cayman Islands. That one's not going to freeze over anytime soon, and they have a post office there. That's the claim to fame of the Cayman Islands and hell. You can send a postcard from hell. So hire an attorney. That's always cost effective. Do nothing. So looking at this one, I can tell you exactly what I did in the next slide. And we called the customer, asked for adapters, contract review, woohoo. Customer indicated to us that what we thought was best. Everything was documented. We put this on the certificate and this is a 2005 standard, not the 2017. And back then, we're showing the dates. This is what we put on the cert. Now we're in ASTM 18, E74 18. But here's what we did. Note this in red. Note, in compression, the adapter was threaded tight against the top of the load cell. An adapter used by Morehouse Instrument Company was threaded approximately 1.5 inches for tension and compression. The zero return values were taken approximately 30 seconds after the load was released. The calibration is in conformance with QAM, blah, blah, blah. So what we did, it's a CYA. It's a cover, or a CYB. We'll see if family friendly. It's a cover your butt scenario. Hey, customer instructed us exactly what to do. They said document it, and then we have to document it. So that's what we did. We did everything. To me, we did everything right. We called the customer. They said they'd fabricate their own. They didn't want to send one. We would have rather them sent one to make sure it was a perfect situation where we knew we could replicate the results, but we used our adapter and we documented. Here's another one, loading through bottom threads and compression. This one's a big one because people don't realize, we are not the end all be all. We do just a small portion of the force calibration that's out there. Believe me, I want to do more of it. There's no other thing to say than I feel we do a fantastic job, and I would like to do more of those jobs for more people because other companies don't do that, and we see it more and more. This one's not a bad thing; it's just something you need to be aware of. So we load. Typically, we're finding about 99% of our customers want to load a load cell this way. That's fine. Nothing is wrong with that, right? If that is you, if you are in the 95%, congratulations. That is our default loading procedure. However, that other 1% want to load it this way. As long as we know and we replicate how it's being used, we're okay. Our competitor, as their standard, they load it this way. They load it the way on the right. So most of our competitors have tension and compression machines where they fixture the load cell up and they fixture it up this way. What does that mean to you? Does it make a difference? It does. And you can see 3 pounds out of 25,000. A lot of people may say, who cares? That's not a big deal. It all depends on what you're looking at and what you want to do, right? So this is a difference of 0.12%. If you're chasing 0.05% of full scale, never going to get there with this. If you're chasing 0.01, never going to get there. So it all depends on what you're chasing. But the main thing is it's repeatable and it's reproducible. So you just need to know, and you need to have the conversation with the lab and know that if you're sending it to one of our competitors, chances are they're thread loading it in compression, and you need to do that. If you want to replicate the results, now you need to thread load. It's pretty much sucks in one aspect because you may not know that. They may not be telling you that. So now you have this 0.012% phantom error that you can easily correct by loading through the top and bottom, or by loading through the threads. Or you can call them and say, hey, anytime you load my load cell, make sure you load it against the base. I want it loaded against the base, and just demand they load it that way. They'll do it. It's a conversation, not a knock. This is not a knock on anybody. It's just know what's being done. So what does that do? Ideally, we're still shooting for this 0.462 out the door. Hey, expected performance of this device is less than half a pound out the door. That's awesome on a 10,000 pound load cell. If this goes out the door and somebody say we load it flat and somebody else loads it through the threads, they're not going to get that half pound. They're going to get 1.461. That's what that does. So just be aware of it. Morehouse threaded adapters can be used for, these adapters that you saw for tension, these can also be used for compression, for loading against the bottom base. We can also put a ball adapter. They can also thread into the load cell and load them against the shoulder, and we can put ball adapters on them. Pretty cool. Again, the best case scenario is just good, better, best. Best is always to have the however the customer's using it, that's best. So on the better side, if you don't have that, these would be on the better side of adapters, just to have it so you can facilitate the calibration and provide a good result and match. You can load it through the bottom threads. You can do that. These are flat. You can solve that issue. You can threaded against the shoulder. Against the shoulder was an 0.1. That one is the better, but you still could have that 0.1% error. So it's something to be cognizant of. Not using different curves for decreasing forces. Had a great guy at the Air Force. Shout out to Willie on this. He sent me this. I love this. This is just all that he was just doing testing. It's just all the different curves, and he's plotting the percent of full scale difference from linear cells. So what's going on here is they're not using different curves for decreasing forces, and you can see what happens. Hey, if I just load it to 50%, what happens on my curve? If I load it to 100%, what happens on my curve? And it kind of looks like a whale. So you kind of call it the whaley, but you can see what's going on, and there's not an all-encompassing. The only thing you can really do in this case is if you're using a load cell decreasing or descending forces, you can use a combined curve. And the combined curve, I know this is foreign to some, but the combined curve really takes all this information. The problem with the combined curve is you have that much uncertainty, right? By taking all the information and plotting it, your uncertainty gets a lot larger. But any point you do within this, in that large span, will be in. What's going on here is saying, hey, if I load it to 60% and come back, here's a curve. If I load it to this, here's a curve. So they're trying to classify things a bit differently. And in fact, in this one, here's the combined is here. But that green that kind of splits the where you're going to load it. But you do have the larger uncertainty because you have that area. All that area is the uncertainty, and you're going to get a point. This green point in the middle for a combined curve is going to say, hey, if you want to use this large error, you can use ascending or descending. Now, elaborate a little more, and I know this is a little confusing. The ascending curve can be used any point in its range, right? You can go to 50% on an ascending curve and you can repeat all day long. That's the nature of the load cell. But when you're descending, the load cell has to be loaded to capacity to come back down. What people tend to do is they can do loops or anything else. But again, it's one of those things that if you just go partially, you're going to get a different answer. And you can see the difference between the ascending and descending curves is quite large. In fact, we see these around 0.5% quite a bit. So do not assume an ascending curve can be used for descending. It absolutely cannot. And just do not assume that your descending curve is valid for every point in the range, because if you only go to half capacity, it's going to give you a much different curve than if you go to full scale capacity. Now, remember when I said earlier about 4 to 6 wire? And this is a cable length error. Load cells used with meters that have 4-wire configuration are subject to additional error. We were talking about the indicators. The Hattie is 6-wire. The 4215 is 6-wire. Guess what? That battery-powered PSD is not 6-wire, so that would have this additional error. So what happens is voltage drop over cable lengths, and the effect on thermal span characteristics of the load cell as temperature changes can alter cable resistance. Problem with 4-wire, if you're using that PSD indicator and all of a sudden your cable breaks and you want to add 10 feet of cable, you're going to have a different output. Substitution of 4-wire cable at a given length with another 4-wire cable of a different length or gauge will produce additional errors. That's really what's going to happen. You're going to have that different thermal characteristic. You're going to have different resistance because you're going on a longer, or you're going to have, if you use a thicker gauge cable, it's going to be less resistance there. So here's what you need to know. If you damage or replace your cable, the system may need to be calibrated immediately following replacement or repair. Operating at different temperatures will change the resistance, which will cause a voltage drop, resulting in a change of measured output. Cable substitution will result in additional error and should be avoided. Cables used for 4-wire systems should have a serial number or a way to make sure the same cable stays with the system it was calibrated with. This would be good measurement practice technique Morehouse highly recommends. What we see here, we see numerous 4-wire systems from various manufacturers come in with multiple cables of different lengths. We will mark the cable we used. We talk to customers. If you want to use a longer cable on a 4-wire system, you should have 2 calibrations, and 2 calibrations is too expensive. in my honest opinion, where you should just change to a 6-wire system. That Hattie is under $1,000. I guarantee you that you would spend more than that on having 2 ASTM calibrations to say, hey, I have a 10-foot 4-wire cable and a 30-foot 4-wire cable. So it really, if you're using a 4-wire system, if you're using any of those meters that are 4-wire and you're switching cables or doing anything, switch to get a 6-wire system immediately on the next cal. Don't continue to do it. Your errors are going to be huge, and we'll, since resistance is a function of temperature, the cable response to temperature change affects the thermal span characteristics of the load cell cable system. For 6-wire, that's eliminated. 4-wire, there will be an effect. It's going to be like 0.01. And it all depends on the gauge. Most things I've seen is about 0.01 per every 10 feet. For every 10 feet would be that would be the absolute best I've seen. A 0.01% change for every 10 feet would be the best cabling change I've seen, and that's usually the really thick ones. If using a 6-wire meter wired properly, this error becomes minimalized. With a 6-wire setup, the sense lines are separate from the excitation lines, thereby eliminating effects due to variations in lead resistance. It allows for long cable runs in outdoor environments with extreme temperatures. Also allows you to have a lot more confidence in your measurement. Wiring a 6-wire cable for sense is easy. You say, hey, my load cell's not wired for sense. There's the diagram. It's as easy as running 2 wires from the load cell's negative excitation pin and the remaining 2 wires to the positive. So you can hook, if you have a meter that does sense, you can wire a cable if you have a standard bridge load cell. The error in class, we used a 4-wire cable, same gauge, 6 feet versus 10 feet. And it produced a 0.106% error. I think that was 22 gauge cable, if I'm not mistaken. That is important to know, and I don't know that off the top of my head, but it was a significant, 22, 24 gauge, somewhere in that ballpark. And just the additional 4 feet produced an error of 0.1. What does that do? So if you're switching systems, if we do the cal and we say, hey, this is good to go at the, under the ½ pound, then you go out and switch cabling. You take that 6-foot cable to a 10-foot cable. That error becomes what you think's a ½ pound becomes 12.249 pounds. So really, really significant, really easy to change. Torque and bolting a load cell. Here's a situation. We ran a load cell, saw the deviations were rather high, and started questioning it. It was higher than what we expected. What we did is we took one of these torque wrenches here, rather uncommon. Now we do it all the time if we have, it's one of our troubleshooting techniques. But so we used a load cell tester. Everything's good. Everything's positive on the load cell. All good. We proceeded to check each bolt and found that 2 bolts did not have the appropriate torque applied. What ended up happening is the person that was putting it together painted everything, torqued everything, didn't realize they missed 2 of the bolts. They painted everything. That became hardened, and no one suspected because it was hand tight versus, torque specification. No one suspected anything different. What we ended up finding out is that the 2 bolts broke loose on a counterclockwise a lot easier than the other ones. So we retorqued everything. After we did that, we found the new was 0.441 pound versus the old, which was 1.43. This was bolts that were torqued. So that's what happened. The deviations after were much less, and it's just one of those things that if you're bolting and unbolting cells, you have a lot more to worry about than just the calibration. You have to worry about R&R between your technicians. You need to worry about the difference in torque values. Most of those wrenches are 4% or better. So you have a lot of variation in that process. Now, this is a common question we get asked a lot, and that's why it's in this slide. We're approaching the end of this, but this is in the slide. We get asked all the time, different excitations, what do they do? This one, that 4215 meter, this was cool because it's real easy. All we did was change excitation. We have the same signal and waveform, just excitation change only. and there was a difference of about 0.01% throughout the whole range. This first point, if you see it at 024, you got to ignore that. That's the 200 pounds. Any slightest bit of resolution change is going to change that output. But you can see down here, it went 411, 258, 411, 296, change, 38 count difference from, 5 volt, 10 volt to 5 volt. Surprisingly on this one, the 5 volt had a little more output. In this scenario, but the meter allowed you to switch voltages. This is what we got pretty consistently. Excitation and waveform is all over the place. So if you're going to switch voltages, you really need to have the cell recalibrated at the appropriate voltage. As part of the traceability chain, if you're applying 5 volt DC, you should have, and you're switching meters, you should have a traceable 5 volt DC traceability on that the whole way through. If you're applying 10 volt, you should maintain amplitude and waveform, all that stuff. If it's an AC measurement, you should use, maintain that. AC cannot be substituted for DC. That's a cool band, but that's Tesla versus Edison, or the band Angus Young, for all those that are, guitar fans out there. I love AC/DC. It's just, AC cannot be used. They're not interchangeable. So the Hattie uses an AC signal, that high accuracy digital indicator, and you can standardize it, you can do everything else, but you can't use it as a voltage reference. That's the big difference. It's not common, but it's a perfect indicator for calibrating your load cells and containing a system. Just not a good load cell to capture, to use as to record millivolts off of the unit under test, unless you are fine with the AC signal. Other error sources not covered: time difference in calibrations and drift of standard calibrations with time. So time differences in calibration is interesting. So the way you apply a force, if you apply, I know what we do. We apply dead weight, and we apply it for 30 seconds. It's timed. We apply it consistently. We wait. Our weights are timed, that it wait 3 seconds between application of weights. So you put one weight on, waits another 3 seconds, waits. So if I'm putting 10 weights on, it's going to be 30 seconds until the force is fully applied. And then once the force is fully applied, we're going to wait 30 seconds until we start taking force points. There is a difference. If we would wait 6 seconds to 30, there is a difference. Now, our competitors, or those using hydraulic frames, a lot of them do not hit the force points exactly. So the problem with the system, not really a bad, they interpolate the points. So at 10,000 pounds, they may apply 9,999. They may hold it for, that hold may vary, and they're just manipulating all of your data. 9,000, and you can say, so what? It's only a pound, but they're applying interpolation curves. The whole problem with what is being done there is the record of raw data. When you see your raw data, you never see that, 9,999 was applied. You see 10,000. The laboratory shall retain records of all that raw data. They're not reporting it to you. So the big question is, are they retaining the appropriate records per the standard? ISO IEC 17025 section 7 and 8 talk about this, and they really need to demonstrate. You have the right as a customer to request that raw data if you want it, and you can verify the manipulation. So that is your right. They are required to take it. I'm not so sure they're doing it, but it's absolutely your right. And it's a problem, because really we don't know. I can tell you what we're doing. It's 30 seconds. The standard ASTM just says as uniformly as possible. They could be doing 5 seconds. So 30 seconds is going to give a little bit different output than 5. And if you want to know, you should ask, how long are you holding this dwell time? Are you holding it 5 seconds? Are you just running up and down through the calibration? These are things you need to know, because you want to replicate that. Whoever's providing you with that reference information, when you're using that cell, you want to replicate it. So, and then also you have the drift of calibration standards with time. That's covered that a little bit earlier. As anything, people say they can age things. This age dating or whatever, it doesn't really work that way. If I calibrate a load cell to 10,000 pounds today and put it on a shelf for 2 years, it's naturally going to age and shift over time. So it's very mechanical in nature. Aged load cells are better than non-aged ones. So, that's something else to consider. You may say, hey, I have this old load cell here that I want to replace. Well, if it's old and functioning very, very well, that thing should be rock solid. All of the drift, everything should be out of it. That's a hard replacement to justify because you have all those years of history. In fact, if you have a really, really stable load cell that's in your fleet for calibration, I'd almost upgrade it to a new load cell and use that one as my check standard, because there's no better check standard than a load cell that has all the history and stability. And if you want that check standard to run statistical process controls or anything else, man, take your best load cell to run that. That is my advice. That's the only time you upgrade it. But you're upgrading two ways. You're upgrading to a new load cell for the field, and you're upgrading potentially to like this master awesome check standard. So it's just another thing to consider. So with that, I'm going to end the recording. I thank everybody for their time, and I'm going